Hi everyone. Okay, so continuing in section 3.3, we want to use something called the first derivative test. The first derivative test basically just determines whether, when you have a critical number, whether you get a maximum or a minimum. Okay, so there's three possibilities here. When you look at the sign chart, right, you have a function f, and if it's differentiable, except that possibly it's c, right, so c is a critical number. In the first possibility here, the derivative changes from negative to positive, right? So remember what a negative derivative means. It just means that you're going down, you're decreasing. And then at x equals c, it changes from decreasing to increasing. Sorry. So what that means is that at x equals c, here you have a relative minimum. Okay, so if the derivative changes from negative to positive at your critical number, you have a minimum. Right, now that can occur because the derivative is 0 at c, or it could occur because the derivative does not exist. For example, you can have a graph that looks like this, and pretend that's at c. Here the derivative would fail to exist, but it's still going from decreasing to increasing. We would still call this a relative minimum point. Make sense? Okay, so now the second possibility, we have this, if the derivative changes from positive to negative. So let's say this is my c. If the derivative is positive, we're going up, and if the derivative is negative, we're going down. So at x equals c, we have a relative maximum, right? Relative maximum at the points at x equals c, and then of course the y-coordinate would be f of c. Right? So notice I drew it here where the derivative fails to exist, but we can also have where the derivative is 0, so it's increasing and then decreasing again at x equals c. Okay, so either way, you have a relative maximum. Okay, now there's two other possibilities. I'm going to draw those down here now. So let's say c is over here, and let's say the derivative is positive to the left, so it's increasing, and then it levels off, but then it's positive to the right. So because the tangent line still has slope 0 here, right, this is still a critical number, but we would not say that this is a maximum or a minimum, right? So when the sign of the derivative does not change, in other words, it's positive to the left and it's positive to the right, not a minimum, not a maximum. It's neither. Okay, so over here at a different c, let's say c2, this is c1. Let's say this happens. Now the derivative is negative to the left, levels off, and then it's negative to the right. So the derivative at c2, because the tangent line is horizontal there, the derivative is 0. That makes this a critical number. On the other hand, you might notice that the derivative is negative to the left and negative to the right. And for the same reason as over here, this is not a minimum, it's not a maximum. So yep, you can have, right, so a critical number does not mean a minimum or maximum. However, a maximum or minimum means it has to occur at a critical number. But the reverse is not true in the sense that you can have a critical number and not be a minimum or maximum. Okay, so I hope that explains the first derivative tests. Let me do one quick example. Find the relative extrema. So by relative extrema, we mean maximum or minimum for this particular function, negative x cubed plus 12x squared minus 45x, right? So the way I would do it is this. So first of all, right, a relative extrema has to occur at a critical number. So we need to find the critical numbers. So how do you find the critical numbers? Take the derivative, right? F prime of x. So the derivative here will be negative 3x squared plus 12 times 2 is 24 times x to the 1 minus 45 times derivative of x is 1, and the derivative of 20 is 0. So that's the first derivative, right? And to find the critical numbers, where does this not exist? Well, the answer is nowhere. It's going to exist everywhere here. So the only critical numbers come from where the derivative equals 0. So we have to solve this equation, and you do it the usual way. It's a quadratic equation. You can actually use the quadratic formula, but I'm going to do it the old-fashioned way. Just factor out the negative 3, leaving you with x squared minus 8x plus 15. Right? And after you factor out the negative 3, you can factor this. What two numbers multiply to 15 and add to negative 8? So it's going to be negative 3 times negative 5 is negative 15. And as a check, negative 3 plus negative 5 is negative 8. So when you set this equal to 0, you get two solutions. You get x equals 3 and x equals 5. I hope you're not saying negative 3. That's not a critical number, right? You can actually divide by negative 3 here. So x equals negative 3 is not a critical number. This is just the leading coefficients. You can divide by it, right? So two critical numbers, positive 3 and positive 5. Okay. And so these are possible maximum and minimum. We don't know that yet. We don't know whether they're really maximums or minimums yet. The way to determine that is to use the first derivative test. Okay, so draw your number line. Let's mark off the critical numbers, 3 and 5, right? And just like in the previous example, in the previous video, we were determining where the derivative is positive or negative. So here's the first derivative, right? And now I wish I didn't erase the negative 3 here. Yeah, the negative 3 is part of the derivative here. Okay. Okay, so yeah, so we determined the sign. We know that the derivative is going to be 0 at 3 and 5, but what about everywhere else? So pick your favorite number less than 3. I could pick 2, but how about 0, since that's easy? Plug that into the first derivative. Well, you're just going to get negative 45, right? You get negative 3 times negative 3 times negative 5, right? So that's negative 45, which is negative. So not just at 0, but everywhere less than 3, the derivative will be negative. All right, what about between 3 and 5? Oh, hey, you know what? Let's do a shortcut here. We know that at x equals 3, the exponent is 1. 1 is an odd number, so we expect the signs to switch. So this will be positive now. If that was too quick or if that's not clear, well, let's do it the old-fashioned way. What's between 3 and 5? 4. Plug that into the derivative. I'll plug it into this. We get negative 3 times 4 minus 3 times 4 minus 5. And that's going to be negative 3 times 1 times negative 1, which is positive 3. So indeed it is positive. And so what happens when x is bigger than 5? Say at 6. Well, you can plug it in, or just note that the exponent here is 1, which is an odd number. Odd numbers means the signs alternate, so this will have to be negative. And if you don't believe me, again, plug negative 6 into this derivative, and you'll get a number that turns out to be negative. All right, so are we okay with that? So now we know the derivative is negative from negative infinity to 3 and from 5 to infinity. Right, so that's the interval on which the intervals on which it's decreasing. The intervals on which it's increasing is from 3 to 5. Okay, but our question was, where do we have a maximum? Right, what are the maximum and minimum? So we use the first derivative test. Right, if the derivative is negative and then positive, we know it's a minimum. Right. On the other hand, if the derivative is positive, then negative, then that gives you a maximum. So we can finally answer the question. We can say f has a relative minimum at x equals 3. Now, I guess the question wasn't really clear. What do we mean by relative extrema, right? We mean the maximum or minimum. The maximum value, of course, is not 3. 3 is where, minimum value. The minimum value is not 3. It occurs at x equals 3. So the minimum value is f of 3. And how do you find f of 3? You don't plug it into the derivative. If you plug it into the derivative, you'll get 0, right? That's what makes it a critical number. You have to plug it back into the original function, right? The original function is way up here. So that's going to be negative 3 cubed plus 12 times 3 squared minus 45 times 3 plus 20. And I'm not sure I feel like doing the arithmetic here. Obviously, you can just use a calculator. So what I think you get is 29. You can double check my arithmetic, right? So the minimum value is 29, right? So the actual relative minimum here, you can, to be complete about it, we'd say it's at 329. Okay. What about the maximum? So again, by the first derivative test, x equals 5 gives you a relative maximum. So f has a relative maximum, forgive the sloppiness, at x equals 5. And what's the maximum value? So we plug in 5 into the original function. That's way up here. Again, if you plug it into the derivative, you'll get 0. That's why it's a critical number. So if you get 0 here, then that would just be a coincidence, right? I don't think you get 0. You do the arithmetic, you get 75, right? So the maximum occurs at x equals 5 and y is 75. So again, on a test, of course, I'll make this clear whether I'm looking for the maximum value or just looking for where the maximum occurs. So two different questions. Where does the maximum occur? At x equals 5. What is the maximum value? 75, right? So if it's not clear, then just put both, because that will take care of everything here. That way you have the maximum point and the minimum point. Oh, yes, remember, Kahn says that, right, this is a critical point. These are critical points. I wouldn't use that language here. 3 and 5 are critical numbers, right? If you want to say these are critical points, that would be a little more appropriate. But I'm going to really try not to use the term critical point. I'm going to say critical numbers. So I hope that helps. And so that gives you the idea of the first derivative test, right? You find the critical numbers, and then how do you know if the critical numbers are become maximums or minimums? Well, you use the first derivative test. So I think I'll leave it at that for now. If you want, in fact, I think I'll do one more example in the next video. But this should give you at least the idea of it.